We're still working our way towards actually defining H, so let's consider the kinds of attacks that H has to resist. One possibility is that you know X and you're trying to find a colliding Y. And so an example use of this is a substitute for a download. Another possibility is that an attacker gets to pick both X and Y. So something that they can convince you to accept X and then later substitute Y. This is a little bit easier than having to work from a fixed X because you could possibly change X and Y in some way to make them collide. So we want to make this impossible, or at least infeasible, as well. Finally, you might know the hash code for some X without knowing X, and we want to make it impossible to reconstruct X from just its hash code. So having the hash code of a document and reconstructing the actual document that I hashed, that is one thing that should not be feasible. Or similarly, if we saved a hash of a password, then you shouldn't be able to reconstruct the password from that hash, even if the password is small on the same order of the hash, if it's 512 bits. So here are some hash functions to be used as H that have the properties we want, or at least had them in the past until some analysis or computational power negated their advantages. MD5 is one of the most widely used. The MD stands for Message Digest, so it's the fifth Message Digest algorithm. MD5 uses a 128-bit hash code, and at this point the algorithm has been analyzed enough and computing power has increased enough that collisions can be found. So MD5 is not considered secure anymore. SHA-1 is based on the same algorithm family, the Merkle-Damgard family. Merkle-Damgard happens to match MD5, that's just a happy coincidence, but it's helpful to remember that it's the same family as MD5. SHA-1 uses 160-bit hash codes, and some collisions have been found for SHA-1. Not enough to make it an immediate danger of being broken, so SHA-1 is still widely used. It is the default hashing used by Git, for example, to map data in your Git repo into hash codes that are used to reconstruct it, so it's important that no collisions happen in practice. The safe bet is that more analysis will lead to more collisions in SHA-1, and so if you want something to be secure for the foreseeable future, then you should consider SHA-2 or higher. SHA-2 uses 256-bit hashes, or 512, so SHA-2 encompasses both of those standards, which are sometimes expanded out to SHA-256 and SHA-512. They're both considered variants of SHA-2, though, because they use the same sort of algorithm, the same sort of variant of Merkle-Damgard. And it is considered secure because 256 is a big hash code, and we still don't know a way to find collisions without just searching that entire space. So SHA-2 is the right thing to use today if you want a secure cryptographic hash. Now, an attack to SHA-2 may be found in the future, and that's what SHA-3 is for. SHA-3 is standing by based on a completely different algorithm family. It generates the same number of bits as SHA-2, either 256 or 512. But since it's a different algorithm, if there are attacks found to the Merkle-Damgard family, then this one is ready to be dropped into place. Because it used the same sort of hash bits, then it would be easier to adapt software to switch over from SHA-2 to SHA-3. So use SHA-2 today, choose SHA-3 if you'd like, but both of those are considered secure cryptographic hashes.